Okay. So as I was saying earlier on, before the disruption, so the Norton, I want to start from the Norton's theorem fully now. The guys on the YouTube can see me now clearly. So I want to start with the Norton's theorem. So the Norton's theorem follows closely after the Thevenin's theorem, only in that the source is now parallel to the resistance, the equivalent resistance. Whereas in the case of the Thevenin's, the source is in series with the equivalent resistance. And that is just the only thing that is the difference in this place. So a good example here, in this place, there is no dependent source. I've told you whenever you see a dependent source, what makes you to know a dependent source is the fact that it has the diamond symbol. Once you see a diamond symbol, it is a dependent source. So if you look at this particular circuit, you have the source voltage 28, you have the resistors there and here, and at the other side, you have another source voltage, 7 volts. But the load is in between. So what you do is that you can resolve it in this way by getting the current, Norton current, in parallel with the equivalent resistance, which is otherwise known as Norton's resistance. And that is what has been done here. In order to get the Norton's current, you can see what is done here. You just use your Ohm's law, V over R, V over R for both sides, and you are able to get your current. And then the Norton's equivalent resistance, you bring together all the resistances with the exception of that of the load, because definitely and obviously you must disconnect the load for you to be able to get the total supply or the total, yes, the total source materials, source parameters. What do I mean by source parameters? That's why we were taught source transformation. So everything with the exception of the load form your source when you are talking of um, equivalent representation, either in form of Thevenin's or in form of Norton. So you are giving this as another example of the with dependent source. You can see the dependent source now, which is a current dependent source, because you have an arrow inside that diamond box. So on the account of that, you can then be asked to resolve this into equivalent resistance or equivalent circuit, in which case you will have equivalent resistance that will just be one unit of resistance, one component of resistance. All the resistances are brought together as one, and you will have one source, either voltage or current, depending on the method you have been asked to use. If you are asked to use Thevenin's, then you will be talking about Thevenin's voltage. If you are told to use Norton, as in this case, you'll be talking of Norton's current or Norton's current. So on the account of that, these are the steps that you normally follow. You will have to set aside the independent source to be equals to 0 and connect a voltage source to the terminal. That is when you are dealing with the dependent source. And then you will ignore the 4 ohm resistance because it is short circuit. Then you will take care of, also due to the short circuit, the 5 ohm resistors, the voltage source and the dependent source are in parallel, because all of them I've told you, when you get to a junction and you have a decision to make, then you should know they are all in parallel. But when you can move without having to take any decision, then they are the current, the circuit parameters are in series. So in this case, because when you get to that junction, you have the dependent source, the 5 ohm resistance, and the 10-volt voltage source. Then you will see that you have 3 decisions to make, and any of these decisions will determine what will happen. So that means the 3 of them, they are in parallel to each other. So this is how it was resolved. You make your I naught to be equals to you make your I naught to be equals to the Ohm's law, V naught over R5 ohms. And that gives us 1 volt, which is the V naught, over 5 ohms, which is the resistance value of the R5 ohms. So you are able to get your current there. And then likewise, you can get your Norton's resistance, which is V naught over I naught, which is still Ohm's law. And by the time you resolve that, you get what you have in this place. So you can see the step 2 as well. Because we are to get Ix, the voltage in the current in uh, the source current for the independent source, the dependent source rather. So the step 2 is that you compute In, and in computing In, you saw circuit determinants A and B. And when you short circuit it, you will have I short circuit there, which is the same thing as In. And likewise, you should know that from the figure that 4 ohm resistor, 10 volt, and 5 ohm resistors, just like as I've said, they are all in parallel. So that's how you came about Ix, which is equal to V over R 4 ohms. And then you were able to get 2.5 amps. Likewise, your Norton's current, which is the same thing as short circuit current, you can obtain it by following the rule that you already know, which is the rule of Kirchhoff current law. So by your Kirchhoff current law, you can go through the system and find out that what is entering into the node will be equal to what is coming out of the node. And that's how we were able to get the V over 5 volt, R 5 ohms, V over R 5 ohms plus 2 IS, because the two of them, they are entering into the same node, and then they are leading to IN or ISC, whichever one you want to call it. So that is your Kirchhoff current law. What is entering into a node must be equal to what is coming out of the node. So that's how you were able to get that 7 amps. So I still explained it further in this place. And then I told you that at the end of it, you must always have two parameters, a current source and a resistor element. So the current source, you have more than two. By the time you are through with your resolution of the problem, you will have two circuit parameters therein. You will have this current source, which will be in parallel with resistance, the equivalent resistance. Just like you have in the case of Thevenin, the voltage source, which is in series with equivalent resistance. Likewise, you will in the Norton's variant, you will have the current source, which is your Norton's current, in parallel with the IRN, which is your resistor uh, equivalent resistance. That's exactly what you have here. And I want to believe this is very very clear enough from the way I have gone from step to step there. Then you may have to look at this particular problem as well. These are some of the problems I'm going to be giving to you, and I'm going to give you under 6 hours to submit them back because I'm going to be sending the question very soon to the platform and then not to this platform. I'm going to be sending it through either Google Classroom or through my V-Learning LMS. Because in some people are still having problem linking to LMS, I may use the classroom after this lecture, and I will just give you 6 hours to submit all the answers back to me. So if you are given this problem now to solve, and you are told to obtain the Thevenin equivalent, I want to give you time to look at it now. Let everybody begin to work. I'm going to give you 5 minutes. So by 8:40, I'm going to call one or two of you to solve this. And if anybody has, so you have 5 minutes to solve this.
So a question. Okay.
Yeah, it's already 7 minutes after. So nobody has raised up his hand. Uh, okay. Oh. However, let me call Father Hero. Is Father Hero there? Father Hero, are you there with us? Akintola. Okay. Akintola, I'm coming. Isaiah, I'm coming. I can't take you because you didn't follow format. You didn't write your name correctly. You didn't follow my format. So you cannot answer a question for me. Anosike, Isaiah, can you drop your hand? You have not properly identified yourself on the platform, please. Adedokun Dorcas. That means these people did not come today, as far as I'm concerned. So I'm marking them as absent now.
Good morning, sir.
Adedokun Dorcas.
Good morning, sir.
So why didn't you answer earlier on?
Sir, you just called my name.
So after I have said that I consider those I have called not to have been in class, that's when you decided to answer. As far as I'm concerned, you didn't come.
No,
As far as
sir.
I'm concerned, I called you earlier before then. Oniloyedowu. Oniloyedowu is not in the class. Yusuf Babatunde, not in the class.
Sir?
Who
Hello, sir.
is
You see
saying?
what today?
Okay, show me what you have done online. Anybody I did not call or permit to answer questions should mute. It's only the person I have called that should not mute.
Sir, I joined the classes. I've not been able to do it.
Number one, you didn't complete your nomenclature. You cannot give me that excuse. You are in your various homes. As far as I'm concerned, you didn't come for today's lecture. And be sure that this thing is being recorded. So if anybody has any case after the out, I will always play this, whoever wants to listen. So as far as I'm concerned, you didn't come to class today. Be sure that this is recorded. And that's why I love this kind of thing. Because we can see, we can hear, you can see my face, and I have the recording of what we are doing here. So there won't be any reason for anybody to say it was witch hunt when he faced the cause and he has come back. Kushimo Oluwatofumi.
Sir, good morning,
Yeah,
sir. Please, sir, give me a minute to send to my laptop.
I can't give you that minute. By now, I have given you more than 5 minutes. I said 5 minutes for the walking, and this is 11th minute after.
No, to send
So
to my
stop using.
laptop. I've done
That's
something
not
just to send.
that's not
I
before
just want to
me,
send
as
it.
far as I'm concerned. That's not before me. You should get yourself ready that anybody can be called. Okay, let me listen to Isaiah Iyang. What do you have there? Kushimo, can you mute yourself?
Good morning, sir.
Yeah.
So, I saw my camera, right?
Yes, on your camera. Let me give you the privilege to. You can share your screen now. I want to drop the. No,
I'm
I
using.
want. I will need to drop my own sharing right so that you can come up. Yes. Okay, you can do your own now. We are seeing your ceiling, the ceiling of your house. So you have to do it. Face it to your lecture note. Face your camera to your lecture note.
Okay, I'll need to turn the camera to the back. Okay, sir. This is it.
Yes, we are seeing
So,
your note now.
this is the diagram. So, first of all, finding RTH, we first of all have to turn off all the independent sources. That is this
Yes.
2 ampere and the 32-volt source. So when I turn off all the independent sources, I got this diagram. That's 4 ohms, 12 ohms, and this 1 ohm here, and then this is the terminals A and B. So you 4 ohms and the 12 ohms are in parallel. So 4 times 12 over 4 plus 12, that's 48 over 16, that's 3 ohms. Then the 3 ohms is now in series with this 1 ohm, making 3 plus 1, that's 4 ohms. So this is our RTH. That's the equivalent resistance of the Thevenin circuit. Then finding VTH. Finding VTH, our VTH will be here since there's no this thing. So finding VTH, I used nodal analysis. So I applied KCL at node A. So I applied KCL first of all at this node, and then I also applied KCL. I said I applied using nodal analysis to solve for VTH. I applied KCL at this node, and I also applied KCL at this node. But first of all, the KCL at this node is I naught entering is equals to I1 plus I2. That's this I1 and this I2. So using nodal analysis, this 32 volts minus VA. So here is VA. So 32 minus VA over 4, that's this 4 ohms resistor, is equals to I1 plus I2, that's VA over VA minus 0, since here is the reference node. VA minus 0 is the same thing as VA over 12. So that's equation 1. Then I also applied KCL at node B. Applying KCL at node B, that's I1 plus 2. I1 plus 2 is equals to 0, since there's no current flowing through this 1 ohms resistor. So doing that, I got that I1 is equals to negative 2 amperes. So imputing minus 2 inside this equation 1, that's this whole equation 1, that's 32 minus VA over 4 is equals to minus 2 plus VA over 12. So I moved the VA to one side. Then I got that 96 minus 3VA minus 4VA over 12 is equals to minus 2. Then 96 minus 4VA is equals to minus 24. Then VA is equals to 30 volts. So therefore VA is equals to the same thing as VTH. That's our equivalent voltage.
Where is your diagram?
This is
You
diagram.
have not done the equivalent circuit diagram. The Venice equivalent circuit diagram. You need to draw it. I'm going to ask someone, Ariori. I want to see your own work as well. So your own now, you are telling me that your VTH is 30 volts.
Yes, sir.
And your RTH is what?
And my RTH is 4 ohms.
4 ohms. Thank you. Let me see your diagram, the equivalent diagram.
This for the
yes, good of you. Good of you. This is the way you should draw it. Thank you. Ariori, share your note now.
Okay, sir. This is by circuit diagram. This is a question we ask to find the equivalent.
You are not audible enough. Oh. Ariori, we can't hear you. Ariori, we can't hear you at all. And your network is showing me that your network is very, very powerful.
This is my circuit
It's
diagram.
as if you are not speaking to your mic.
This is my sir.
I know it's as if you are not speaking to your mic. Because I can see that your signal is
sir,
very,
this is my circuit diagram.
it's high in quality. Speak to your mic.
Okay, sir. Can you hear me now?
Yes, very clear.
Okay. This is my circuit. This is my circuit diagram. I first look for my Thevenin's voltage.
Resistance.
By
Okay, voltage.
Thevenin's voltage by removing the load resistance. So the first thing is removing the load resistance. I have this, and using mesh analysis to find the current flowing through this 4 ohm resistor, so I can subtract it so that I can get the voltage at this junction, because I'm trying to use this loop. So from here, I can say this from mesh 1. I say 32. That is from mesh 2 now. The first thing is that this mesh 2, this is a current source, and this is an open circuit. which means no current is flowing through this 1 ohm. And that indicates that the current through this 2 ampere from the direction of my current 2 is equals to -2 ampere. And for this first mesh, mesh 1, so I calculated it like using mesh analysis. So this is 34 volts minus 4 I1 minus 12 I1 minus I2, and the I2 I got is -2. So that is what I did here. 34 volts minus 4 I1 minus 12 I1 minus I2 equals to 0. That is using KVL in mesh 1 or in loop 1. So I've gotten my I2 to be equals to -2 ampere. So inserting -2 ampere there, I got my I1 as 0.5. It is 0.5 ampere. So from this diagram again, moving from node B like this, going to node A. So I made, if my node B equals to 0, I grounded it using a nodal analysis from node B. So these are all node B, since no single resistor there. So from node B like this, then node C equals to 32 volts. Then coming back here, that is 32 minus 4 times I1, which I got, which is 0.5. So 32 minus 4 times 0.5, which is what? 30 volts. So the 30 volts here. So that is what I did here. So this is just my voltage.
So your Thevenin voltage now is what?
My Thevenin voltage is 30 volt now.
What of your
So
resistance,
for my
equivalent
Thevenin
resistance?
resistance, I switched off all the independent sources by short-circuiting the voltage
Your
source.
speaker,
Yeah.
your mouth is far from your speaker again. No.
Oh.
You have muted yourself.
Okay, sir. I switched off the.
Okay, it's louder now.
I switched off the voltage source by short-circuiting it, and the current source by open-circuiting it. So the resistance over here is equal to 4 ohm parallel to 12 ohm. Then both of them are now in series with the 1 ohm resistor, which I did here, 4 ohm parallel to 12 ohm, which are in series with 1 ohm resistor, which is this 4 times 12 over 4 plus 12 is 1. So 4 times 12 over 4 plus 12 is that is 16. The 4 times 12 over 4 plus 2, that is 3. So the 3 plus 1 equals to 4 ohm. So this is my circuit. This is my Thevenin equivalent diagram. 30 volt connected in series with 4 ohm.
But you and Isaiah Inyang, you did wonderful works. And you can see you don't need to attach your load. You can just leave your Thevenin equivalent as it is, because your load is not part of your Thevenin equivalent. Okay. So you just say my Thevenin equivalent circuit is just the voltage source and the resistor 4 ohms. So you don't need to put the RL. Do you get me now? That's number one. Number two, you like, I appreciate you. You and Isaiah, you got the same answer. But if I happen to be a student, Isaiah made it so easy for everybody to understand. But you went to high level. You use a lot of high level languages in order to achieve it, which is good. I'm very appreciative of it. That the two of you work through different means, you got the same answer, and you follow principles. You didn't just get the answers, but you follow the necessary principle. I'm very proud of the two of you for what you have done. However, Isaiah, I hope you are listening to me, Isaiah.
Yes, I can hear you.
Yes, you guys, you did a wonderful work. I'm very proud of you. Very, very proud of you. However, I taught you something that you didn't, none of the two of you used. I taught you source transformation. Ariori, bring up your original diagram again. Let's see your original diagram again.
Okay, sir.
Do you believe you can use source transformation here?
Yes, sir. Yes, sir. Yes, sir.
Why did you have to go through that? Okay, tell me the first step. If you are using source transformation, what will you do first?
This voltage connected in series with
Good
the
of you,
resistor.
good of you, good of you. Very good of you. That's it. You should have just made that one current source and in parallel with resistors.
Yeah.
And the two resistors now, you can parallel them, or is it not possible?
It's possible, sir.
So why didn't you think along that direction as well? You have done a wonderful work. Oh. I'm not, I appreciated and I commended the two of you. But you went through a long process. It's good. But in the exam, you will have all the time. So you should think of 2-3 methods and look at the one that will be. It's not only one method that can solve circuit problem. The principle, once you follow the principle, you and you will get your mark. Those who will not follow the principle that will get such. So if I were you, immediately I saw it, you still went through case mesh analysis, KCL, and the rest. It's good, very wonderful one. For classroom environment, I've done a great work. But in the exam hall, I'm just appealing to you. You know this method now because you told me now what you will do. Then after you have done that, what will happen next?
Okay, sir. So that is the current source.
Do you want to quickly work it for us now?
Okay, sir.
Just open to the next page and work it. Let's see.
Okay, let me.
And likewise, Isaiah, you can work it as well. Your own method is very simple and very few lines, but at the same time, you didn't use source transformation. Isaiah,
Okay.
do you agree with me?
Yeah. So modifying the diagram.
Yes.
So I have this in parallel with the resistor, which is 4 ohms. So also in parallel with 12 ohms. Then in series with 1 ohm. So the current will be equal to the voltage.
But you still have one source voltage there. So one source current.
Okay. This okay.
After the yes.
So this is a 2 ampere, and then so for this is equals to the voltage divided by the resistor, which is 32 divided by 4, which is 8 amps.
Good of you, good of you, good of you.
So for the current over here, for this resistor, I can see there the resistors are parallel. Let me 8 ampere. So combining this resistor, I have what 4 times 12 divided by 4 plus 12, which is equals to 2 with 3 ampere.
16.
Which is equals to 3 ohms.
Okay,
I have
yes.
3 ohms. So I have 3 ohms like this.
Good of you. Good of you.
So also you got in parallel with 2
amp.
In parallel with 2 amperes. 2 amperes. That is this current source. Then in series A and B. So this A and B, they are in parallel with 3 ohms. So the same voltage across 3 ohms is the same voltage across A and B.
Good of you, good of you, good of you.
So I can determine the voltage here by considering by doing the KVL. Oh, no. Okay. By using the mesh analysis, I think the mesh analysis will be the best. Because if I take the current...
You like this or mesh analysis too much. Look at you. 2 currents are pointing to the same source. to the same junction.
Okay.
What happened to them?
Oh.
You have two currents. They are not pointing even opposite each other.
Oh.
What is your own?
Okay, both of them
You
are
make this your mesh
entering
too
through
much.
current. Both of them will be entering through this current due to KVL. So my total current will be equals to 8 ampere plus 2 ampere, which equals to 10 ampere. So my voltage equals to IR, which is 10 times 3, which equals to 30
Both.
volts.
Is it not the same thing you are getting with what you have gotten before?
It is, sir.
You can see. And look at what you did. You didn't even spend up to 2 minutes. And I gave you 5 minutes to solve that problem initially. So you can see how short it is. That's why I kept on repeating source transformation. When I was reviewing with you, I said I've taught you source transformation. I have taught you source transformation. So what is your resistor now? Our resistor, are we okay with our resistor? Because we were getting 4 ohms for our resistor. So we will need to look at that. But I can assure you that you can use your source transformation to get that. Your source transformation has been able to get you the voltage.
Doing my resistor.
Ariori, what are you saying?
The opening circuit.
You have not been able to get us your equivalent resistance. So, Isaiah, do you want to help him?
Yes, sir. There's a 1 ohms that did not write.
Sir, there's 1 ohm over here, 1 ohm. So the 3 is a series with the 1 ohm, which is equals to 4 ohm. So RTH equals to 4 ohms.
Great. Wonderful guys. I'm very proud of you. And in fact, I do not go against, you may not even use that method. The method you use for getting your resistance in your initial work that you did is still valid here.
Okay.
Do you get what I'm saying?
Yes, sir.
Where you short some sources, you open some sources depending on the nature of the source. You remember?
Yes, sir.
So you can still recall what you have done there and bring it back here. But what I'm telling you is that you can get your voltage in a shorter time. You know, it was voltage that took you time in your problem.
Yeah.
The first method that you use, can you remember?
Yes, sir.
That you use mesh analysis, you use KCL, and you were able to do a number of things following each other. But I'm trying to tell you that with source transformation, you can bring this together and get it easily. But the method you use for getting your resistor in the initial stage, it was not bad, it was not long at all. You got it, I think, 2 lines or 3 lines.
Yeah.
Do you remember?
Yes, sir.
So you can still make use of the same method. But if you want to use this method that you have used as well, once you can give the principle behind it, I don't have any problem with it. So this is what circuit analysis is all about. I'm going to give you some problems that will give you 6 hours to solve. But meanwhile, thank you. I see some hands coming up, but I may not be able to ask you because we want to go to the last part of the lecture for this morning. Thank you all. So let's move on to the last part of this lecture. It's not the one. Okay. This is the one. I will have helped you to solve some of these notice problems, but I will raise them together when I'm sending you your assignment. If you don't get the assignment today, you will get it tomorrow, and it's going to be for just 6 hours. So we want to move to the last part of this particular theorem for today, which is maximum power transfer theorem. Maximum power transfer theorem is a very useful theorem that we use in engineering to solve a number of problems. It is highly practical. You will do it in the laboratory, but it's better for us to do it here before you get to the laboratory. I say here that why for electric utilities, minimizing power losses in the process of transmission and distribution is critical. For you to be efficient, you want almost everything you send to get to your supply, to your consumers. Just the same way I am speaking to you now, I want every statement I am making to get to you loudly as if you are in my office with me. So the same way in electrical engineering, we want whatever power supply to get to the load end without reducing the quality, without any form of reduction in capacity, without any form of reduction in quantity. So everything we send, we want it to get to the end from the source. Whatever we send from the source, we want it to get to the end without reducing. We want it 100% at the end. But at times, it doesn't work like that. So on the account of that, and that's why you always work for efficiency. Now, we always say that efficiency, you can't have 100%, but you can be close to 100%. So in some areas, the ability to get the maximum power that you are transferring to reach the end is very, very crucial, like in communication. When Ariori was working problem this morning, I told him I couldn't hear him clearly. And likewise, every other audience could not hear him audibly and very loudly. But he will be hearing himself clearly where he was, but it is just the transmission process. So in this particular area, we are looking at how we can make sure that maximum power is transferred from the speaker, from the source to the receiver, from the sending, or from the sender to the receiver, or from the sending end to the receiving end. So that's all we want to look at here. And we'll look at some mathematics. It's a very simple thing. What you have learned under Thevenin will be very useful here. So for electrical application with electrical load, such as loudspeaker, antenna, motors, it is required to find out the condition under which maximum power will be transferred from the circuit source to the load end, from the sending end to the receiving end, from the sender to the receiver. So that's the essence of maximum power transfer. So we normally have a diagram like this, in which you have your Thevenin equivalent circuit, and then you have the load connected to the end. The condition for maximum power transfer is that your load resistance must always be equal to your Thevenin resistance. Take note of that. Load resistance must always be equal to Thevenin resistance. That is the condition for maximum power transfer theorem. That is the condition. And this is how we normally do it. The load current I equals to VTH, which is Thevenin voltage, over RTH, Thevenin resistance, plus RL, which is Thevenin load resistance. And then the power delivered to this load is equal to P equal to I squared R. You know this very well. Where I is already VT over RT plus RL. So I can now be rewritten as VT over RT plus RL in bracket raised to power of square. Then you multiply by that R, which is RL in this case. And if you work that, look at the condition. The condition for you to get maximum power is when the derivative is equal to 0. And you can see how we did it. The P, that is derivative of power with respect to RL over the derivative of RL, which is the load resistance. We said the two derivatives, the quotient of the two derivatives must be equal to 0. And if you apply that to P that you have as I square R that you have calculated there, you will be able to get what we have in that line, which is equal to 0. Then simplifying the above equation, we get what you have on the next line, which is equal to 0. Therefore, that's how we were able to establish that RL is equal to Thevenin's resistance. RL is equal to Thevenin's resistance. So this is a good example. We will find the value of RL for maximum power transfer in this circuit and find the maximum power. So this is how we worked it. First of all, we remove the load. You can see RL was removed. So we have this there. And then you begin to work it out the way you already know how to work it. And so for you to get your equivalent resistance, all the sources, you short circuit some, and you open circuit others. You short circuit some, and you open circuit, you short circuit the voltage, and you open circuit the current, and you can see how the RTH is obtained. Can you see that? So after obtaining the RTH in that way, you can go ahead just like what you already know to obtain your VTH. And then with that, you go ahead to calculate to get the Thevenin voltage, VTH across the terminal, AB, apply the mesh analysis. So that is what is applied here in order to achieve that. And mesh analysis became necessary here so that Ariori, you will not be confused. In this place now, there is a 3 ohms. That 3 ohms will not make it easy for you to apply the rule that we applied where we did source transformation the other time. It's not as if you cannot do source transformation here, but there may be a little, it will be longer than this process of using the mesh analysis. So I'm not totally discouraging your mesh analysis approach. So you can see after applying mesh analysis, we were able to get the I to be equal to minus 2 over 3 amps. And so the Thevenin voltage was then obtained as 22 volts. So for the maximum power transfer, we have said that the condition for maximum power transfer is that RL must be equal to RTH. And since you have gotten your RTH as 9, what is our RTH now?
12 ohms.
It's 9. It's 9. It is not 12 ohms. Are we
It is
together?
supposed to be 9, sir.
So not 12 ohms. So this is correct. This is wrong. I got it right on the next line, but I made that mistake here. So it's supposed to be 9. So 9 ohms, and then that means your RL equals to RTH is 9 ohms. So in a number of times, you will not be given your RL, your load current, your load resistance. You may not be given, but you will get it once you get your Thevenin resistance. So don't ask questions that, they said I should calculate this, but nobody offered me the value of load resistance. The condition for maximum power transfer is that the load resistance is equal to your Thevenin equivalent resistance. So please don't forget that. And by the time you get that, you can see the maximum power transfer formula, which is VTA squared over 4RL. That is what gave us that. Okay. I think my other question will be, you are going to solve
I'm sorry, sir.
Yes, go on.
Sir, can you help me go to the very next slide? I saw something. When you took the KVL around loop 1, the very next one.
This one?
Yes. When you took the KVL around loop 1, you used 12, positive 12 as against negative 12.
Loop 1.
Applying mesh analysis across loop 1. It's supposed to be 6.
Okay. V12 volts.
Yes, negative
plus
12 volts, not
6 plus. You know, I normally tell you something, that if whatever one you use, if you are wrong, you will get negative. If your direction is wrong, you can see that if you look at what I've done, at the end of the day, my I1 became negative. Inyang, are you with me?
Sir, you went clockwise.
My I1 became negative. That means I should have reversed the direction with which I used my V12. So you are very correct. It will not affect the value. Do you get what I'm saying now?
Yes, sir.
Or I'm not getting you right?
And what I'm trying to say is that you actually, for that 6 and 12 ohms, when you took the mesh analysis, you followed it clockwise. That's 6I1 plus 12I1 minus 12I2. So you actually went clockwise. But when you now dealt with the 12-volt resistor, you went anti-clockwise.
12 volts.
So that 12 is supposed to be negative 12, not positive 12.
For which one?
That's
the
the
6
first
and
loop.
12.
No, the 12 volt source is supposed to be minus 12.
And that's
So
what I'm telling you. I agree with you. But my answer had already confirmed what you are saying. Because I went that way, look at what my I1 is giving me now. My I1 is giving me a negative answer. Am I communicating?
Yes, sir.
Because I told you when we were looking at circuit analysis, I said, don't worry, your quantity will not change once you are following the same pattern. The only thing is that if you misstep by using your positive as negative, if you are taking a direction and positive, you use it as negative. I said your answer will reflect it, that you're supposed to have taken the other way around.
Okay.
Does it make sense?
I have a question.
Okay, walk it over
I
there
have a
and let me
question.
see. Walk it over there and let me see. Let me see what we are bringing out. Ariori, are you Isaiah?
Yes, sir. That's what I'm doing.
Do it and let's compare our answers to this. Why I take other questions. Any other
So
question,
I
I
have a
can see
question.
another angle.
I have a question, sir.
Go ahead.
I didn't understand that why I2 is 2 amperes. Isn't it supposed
I
to be
can't hear
minus 2
you.
amperes? I didn't understand why I2 is 2 amperes. Isn't it supposed to be minus 2 amperes? I2.
I2.
Yes, sir.
Can anybody explain that for us? Ajani Abdulmajid.
Yes, sir. I'm here,
Why
sir.
is I2 equals to 2 amps and not minus 2 amps? That's the question Ilumari is asking. Ajani, you don't know?
I didn't get your question, sir.
He said, look at our circuit diagram.
Okay,
Can you see the circuit diagram?
I can
Now,
see it, sir.
when I go to where I was trying to solve for the Thevenin voltage, that blue line, the first set of blue lines.
Okay.
Are you with me? I wrote
Yes, I'm
since
with.
I2 is equal to 2 amps. But Elumaro is now asking, why didn't I use I2 equals to minus 2 amps? Can you answer that question? Looking at what is on the circuit diagram and where I wrote since I2 is equal to 2 amps. That means you have not been part of this lecture. Ariori,
Sir,
Ariori.
sir, sir.
Yes, did you get my question?
Yeah, yes, sir.
Explain it.
Okay, for this thing, the direction of the current we are taking is opposite the direction of the
Thank you.
current.
Elumaro, did you hear?
No, I don't understand, sir.
Okay. Ariori, can you speak up so that you can
Okay.
hear?
Is taking, if you look at the direction of the mesh current I2 around the 2 ampere, we see that it is going in the down direction, while the direction of the current, the actual direction of the current is going up, but the direction they are taking is down, which are in opposite direction. So due to the analysis, we take that, okay, the current is -2 respect to what we are taking.
Yes.
But if
Elumaro, what happened is that what Ariori is saying, which I've told you in this class, is that if the I2 is pointing on the same way as the 2 ampere, the I2 will be negative.
okay, sir.
Does it make sense to you now?
Not very sure, but
All of them
fine.
are
Sir, the network was bad the other time. I'm back home.
Hello, please. Concerning what Doctor was saying, does it now mean that when I2 is in the same direction with two arms, so it will take positive, or be negative?
Yes.
I didn't get that
Yes,
part.
yes.
Okay. Thank
So
you.
your mic is muted. Your topic just muted.
So we are going to end the lecture at this point, but I have some assignment for you, which I will put on the Google Classroom, because a number of people who are just joining us, they don't have LMS facility yet, and they must be captured. The assignment I'm giving you, you will get it by tomorrow morning, and it will be up for 6 hours. Anybody who doesn't work the problem and submit within that period is on its own. We have gone beyond half of this class, but for the benefit of the direct entry, and we have to give you more problems to solve so that they can go back to the note and solve problems. Thank you. Do have a wonderful, wonderful day. And I must take note.
Excuse me.
I must let you know, I have attendance of those who attended this class. I know I have called names at random. A number of you have failed woefully. If you don't work hard in this exam, they do fail this course. And if you don't believe me, come and check on the class. Go and check on our notice board. A class there should not be anything less than 800. There was only a day. I know I'm being recorded, so that if anybody at the top, maybe the vice chancellor, the deputy vice chancellor, or any other person, even the dean, if they want to ask questions, I will play some of this record to them. The number of you don't attend lectures. We have never been up to 500 at any point in time. I created YouTube for this so that if you cannot join after 300, you'll be able to join through the YouTube. The number of you have not attended lecture at all, and everybody can see those who attended lecture. I'm not asking anybody for anything. No, I'm not answering any question today. So just drop your hands. So by the time you are going to have tests next week, go and prepare yourself up to maximum power transfer theorem. The first test will be coming up. After that test, I will go to the second part of this lecture. And then we will guide you when the time for laboratory workshop will start, so that you will be coming in batches for the lab. But be sure that in this January, you will start your lab. So these are the information I have for you. Do have a wonderful week. And you will see my assignment by tomorrow, which will submit under 6 hours.
Please, good morning, sir.
So we will go to the other lecture, the other part of the lecture.
Sir, how do we students get the assignment?
Please, and again, the slide, this particular
I won't give you any slide. I gave you textbooks when we started. I'm not giving any slide if you could not write notes. That's why I was calling students to work problem for me, because I believe when I saw a slide, you will jot. And I said this from the very beginning of the lecture. I will not share my slide with anybody. Because if you are in the physical class, I'm supposed to be checking your notes to be sure you copy notes. A class that is supposed to be more than 600 and less than 300 is in class, and you want me to be giving slides. That will not happen. So if anybody has not, go and get any circle analysis textbook. I gave you a list of textbooks when we were starting. Go through the study package that I gave to you. There are enough textbooks there, and they are available online. Go and download it and use it for your own use. Thank you. This is a university. You have to give notes during the physical, and I will check whether you copy note. If you don't copy note, I send you out of my class. And I think I said this at the beginning of the lecture. Those who are asking that question will be people who didn't start the lecture with us. So Aibu, what do you want to say? I saw that you wanted to say something.
Good morning, sir. Sir,
Yeah,
please.
how are you?
Fine, sir. Happy New Year, sir.
Same to you.
Sir, please, for the assignment, can we do it in a paper and then snap the paper? And
yes, that's you are not bringing it to campus. That's why I said I'm going to put it on Google Classroom. You will download it from there and you will submit it within that 6 hours. There are going to be about 7 to 9 questions that you will sit down and you will solve, and it's going to be within 6 hours. Okay, and you will snap it and you will upload it. If the time lapses, you cannot submit any longer.
Okay, sir. Thank you, sir.
Yeah. So you don't need to come.
So, sir, we have another.
So how will GD get the assignment, sir?
Yeah?
We have another assignment.
We need
to
okay, the previous one I gave to you. You mean the previous assignment I've given to you?
No, sir. Good morning, sir.
All the previous assignment I've given to you, you will submit them on the platform as well. On the same Google this thing. You may even start with that by submitting those ones first. Then you can submit the extra one later. The major one.
Good morning, sir.
Yeah.
Yes, sir. Sir, tomorrow we have an assignment to submit. So we don't know the time your assignment will take, so be able to plan very well.
That's not before me. I am saying it now that you have to submit, and you will submit that tomorrow.
Yes, sir. What time is this starting from?
What time are you submitting that of tomorrow?
Just physically tomorrow. We don't know the time, but to meet in school early, sir.
Okay. I may put my own between 12 p.m., 12 noon, and 6 p.m.
Yes, sir. Thank you, sir. Thank you, sir.
Okay. Any other question?
No, sir.
Direct entry students, how will you get to upload if you have assignments?
Somebody has asked, how do they get to upload? I tell you, upload it on the classroom. I will have used LMS, but I received message from not less than 30 of you that you have not been assigned opportunity to access LMS. And I have tried to get in touch with my people. I've tried to get in touch with my people there, and I know they have worked on it. But meanwhile, there are some of you that are just DE students. There's no way DE student can enter into our portal on LMS.
Yes, sir.
So we have to use the Google Classroom to submit the assignment. So what I will do is that the previous assignment, I'm going to create a Google Classroom today. I will send the link to your class reps. They will share it with you. The previous assignment, you must submit them today before 12 midnight. I'm going to open it from 9 p.m. till 11:59 p.m. tonight. So all the previous assignments that I've given to you, you submit them today. The only assignment I need tomorrow is the 9 questions I'm giving to you now. If you submit that today, if I'm submitting it tomorrow, I will not grade it for you. I will only grade the one of 9 questions that I'm sending tomorrow, and will grade them for tomorrow. So those assignments I've given to you, you had enough time to have done them. So the platform will be open from 9 p.m. to 11:59. After then, nobody can submit. Then the other one will be open by 12 noon to 6 p.m. But the assignment, okay, everything you will see there. So thank you. Have a great day. Bye-bye.